Everyone, hello my friend, and let's keep starting the questions on the operational amplifier. Yeah, as I mentioned previously, it's a good habit to write the value to the diagram, so it make our our solution much easier. Okay, yeah, RB is 180 kilo ohm, and RC VOB 15 kilo and the beta equals 120. Okay, so the first question is asking us to calculate the uh, Q point value for the IC and the VCE. Okay, we don't know the IC, okay, but we know IC equals beta times IB. So if we can get the value of IB, we can get the value of IC. So how to calculate the base current? Okay, currently we know, yeah, the base current should flow in the base. Here is base, here is emitter, here is collector. Okay, and we know at the left side of the base resistor is 0.85, and we know VE equals 0 volts because it is grounded. And we already know from the question, which is VBE equals VB subtract VE equals 0.7. So do be attention. You should remember or know the difference between potential and voltage. Voltage is the difference between potential. Okay? Yeah. So we know VE is 0. So we just assume the BGT is working in the active zone. Okay, so VB equals VE at 0.7, which is 0.7 volts. Now it's quite straightforward for calculating the value of IB, which is VBB subtract VB divided by RB, which is 0.85 subtract 0.7 divided by 180 kilo. So the final result is 0.83 micron ampere. Micron is 10 power minus 6. Okay. Now we know the value of IB and we know the value of beta, which is 120. So we know the value of IC, which is beta times IB, which equals 120 times 0.83 micron, which is 0.1 milliampere. So we got the value for the IC. So how to calculate VCE equals VC subtract VE, which is VC, okay, because VE is 0. So what's the value of VC? Okay, VC equals VCC subtract IC times RC. We know VCC is 3.3, okay, 3.3 volts. So 3.3 subtract 0.1 milli times 15 kilo, okay. Now it is 3.3 subtract milli will be removed by the kilo. So it is 1.5, which is 1.8 volts. Okay. So now we get the value of VCE, which is 1.8 volts. Okay. Let's test or verify our assumption, which is the BGT is working in the active zone. Now the VB is less than VC. VB subtract VE greater and equal than the 0.7. So it is working in the active zone. Our assumption is correct. So we solved for the first question. Now let's move on to the second question. It is asking if our transistor is working in the active region. Of course it is. We just prove it. So the question 2 is also solved. Let's move on to the question 3, which is asking us to calculate the transconductance Gm, okay? The Gm. All right, we know the definition for calculating Gm, which is minus IC divided by Vt. So Vt, what is Vt? Vt means Kt divided by Q. K is a Boltzmann constant. T is a Kelvin temperature. Q is 1.6 times 10 power minus 19 C, right? C. So in the room temperature, yeah, the Vt barely means 0.026 volts. Okay, now we get the value of IC as mentioned in the previous question, 0.1 milli divided by 0.026, which is, yeah, the result for the value of Gm, which is 3.85 milliampere per volts. Okay, that's the answer for question 3. And for the last question 4, it is asking us to calculate the gain. Okay, calculate the gain. So we also start from the definition of the voltage gain, which is voltage gain equals output divided by input, which is minus Gm times Rc. We know the value of Gm, which is 3.85 times Rc, which is 15. Okay, yeah. So this is milli. Okay, this is milli. This is a kilo. Milli will be removed by kilo. So 3.86 times 15, which is minus 57.6. Okay, sorry, 0.7. Yeah, that's a basic idea. So finally, you will ask why AV equals Gm times Rc. Why? Because we can get this thing from definition. This is IC, this is Vt times Rc, which is IC times Rc divided by Vt. Okay, so this is our output voltage. This is input voltage. Okay, yeah. So now it is a definition for voltage gain. Okay, AV. All right, I think we get the question solved. Hope you like this video. Yeah, my friend, be happy and be healthy. Thank you very much. Bye bye.